Prop 42 says to construct in a given rectilineal angle a parallelogram equal to a given triangle. So in other words, if you're given some triangle, ABC, and then you're given some arbitrary angle D, basically all that we're trying to do is we're going to try to create a parallelogram that contains angle D and has an area equal to our triangle ABC. Okie dokie. And this is kind of a cool one. I think it's a clever proof. It's an interesting sort of problem. And I think it also sort of starts looking a little bit like some of the what they call the classic problems of ancient Greece, which were, what were they all? Squaring the circle, trisecting the angle, and doubling the cube. So all which kind of, in my opinion, seem almost like, I mean, it kind of makes sense why they might think about like, hey, is this possible? But they also seem a little bit arbitrary. And this one too, it feels somewhat arbitrary, just kind of like a strange arbitrary construction, like, hey, do you think this is possible, sort of thing, which I think is interesting. And that's, that's the creative side of math, is thinking about those sorts of problems and whether or not it's possible to solve them. And some of them are not possible to solve, which is why the classic problems were so famous. Because as I recall, using just purely Euclidean construction, you cannot solve those problems. This one you can solve with Euclidean construction, though. So, all right, how are we going to do it? So it's construction proof. So first thing that we'll do is we will bisect BC at E. Let's see, and I already put a line on here, but I guess just to kind of illustrate how I did it, because my intention was to save a little bit of time on this video, but the way that I found this line, by the way, is I just made a radius of BC, and then I put a little mark up here at the top, and then another mark here at the bottom, and then I did the same thing, but with the center at C, another mark here at the top and one at the bottom. I joined them and I found where they crossed the line. It was right where they crossed BC. It was right here. So this is E. So that's that's the bisection of BC. All right, so bisect E, and we'll join AE is the next step. Let's see. And I'm tempted to make this a dotted line because it's not going to actually end up being part of the end construction, as I recall. We'll see when we get there. Maybe I shoot myself in the foot by doing that. All right. So there is AE. What do we do next? Right, so next it says on the straight line EC and at the point E on it, let the angle CEF be constructed equal to the angle D. Right. Okay. So basically from E and in the direction of C, we want to construct angle D. Okay, come on. This is a great compass, but the problem is that it's so sturdy, it takes a while to change the angles. Here we go. So I'll do this, comes up here-ish. And I had made this mark as well. Again, because I thought, oh, maybe I should do some of this work before I start actually making the video. Save a little bit of time, and then I thought, well, part of the reason that I like doing this is doing some of these intermediary steps on video. So here's the point right here. This I will make a solid line. I believe I want to extend it as well. Extend it just a little bit there. We'll see. All right, so there was that. Right, so I better say that. So construct CEF, angle CEF, such that angle CEF equals D. Right. So that was prop 23. Now that I think about it, I would like to also justify bisecting. I don't remember which one that was. I'll see if I can find it really quickly here. Because it's not... there we go, it's prop 10. There. Yeah, that is not cited in my book, and I think that that should be cited in my book. So that's prop 10 that allows us to bisect a line, prop 23 that allows us to copy paste an angle. So here, this angle right here that I just made is equal to angle D. I guess they look a little bit off, don't they? Ah, yeah, it's close enough. It's probably more that my line, I didn't get my line very accurately on that point, but it's close enough. Right. And then next we need to draw through A, we need to draw AG parallel to EC. Okay. So I'll just kind of eyeball that rather than go through the construction because I think that one takes a few extra steps. Let's see. So I guess I'll kind of make just like a faint line for now because I don't know exactly where these are going to meet. So we'll just make the faint line there. And yeah, that's close-ish. Having some trouble today, apparently. It's one of those days. Maybe that's better. All right. AG parallel to EC. Yeah, okay. So I'll just write that. And that was prop 31 that allows us to do that. Okay. And we're going to draw another parallel, as I recall, through C parallel to EF. Yeah, so this is going to be F up here, I believe. So we're going to draw CG parallel to EF. And again, I'll just kind of eyeball it. It's almost exactly the width of my ruler. Just trying to make these lines a little darker. This is pretty good. I don't know, it's not amazing. It's not perfect. It's not as perfect as I would like it to be, but maybe someday, in a decade and a half, I'll re-record this. Okay, so construct CG such that CG is parallel to EF. And again, that was prop 31 that allows us to have that. Well, then, because we constructed EC is parallel to FG by construction, and EF is parallel to CG by construction, it follows that FECG is a parallelogram. And moreover, it's actually the parallelogram that we wanted to construct. So we want to, I guess, my claim is that FECG is equal in area to triangle ABC. So let's prove that. And obviously, FECG has angle D built in, like just by construction, that's already built in there. So that part of the requirement is fulfilled. We're good to go. All we need to prove is that FECG equals triangle ABC, their areas. All right. Well, since BE is equal to EC, triangle ABE is in the same parallels as AEC. So since BE equals EC and triangle ABE and triangle AEC fall in the same parallels, they're equal. And that was Prop 38. Yep, 38. um, but note that triangle ABC is the sum of triangle ABE and AEC. So since triangle ABC is equal to ABE plus AEC, we have that triangle ABC is double triangle AEC. And it's double triangle ABE as well, but AEC turns out to be the kind of key triangle that we wanted to look at to finish off this proof. Okay. But parallelogram FECG is double triangle AEC, since they share a base. And fall in the same parallels. Thus, oh, and I guess I need to justify that. That is Prop 40. Looks like that one didn't get cited either. Was it 38 again? No, 41, right? Because parallelogram FECG is double AEC since they're in the same base and the same parallels. Yeah, that's Prop 41. That was also not cited in my text, and I think it should have been. All right, so FECG is equal in area to triangle ABC, because both triangle ABC and FECG are double AEC. So they're equal. And that's the end of it. We have proven what we needed to prove because the triangle or parallelogram FECG is equal in area to ABC, and it contains, by construction, angle D. QEF.